Jai Hind everyone. Myself Dr. Sharma from AKGEC Engineering College. My subject is Engineering Physics and the topic which today I have taken for discussion, that topic belongs to quantum mechanics. And from quantum mechanics, the topic which I have taken for today's discussion, that topic is actually the main topic, or you can say that is the heart of quantum mechanics. So topic is Schrodinger equations, Schrodinger wave function, its physical significance, and the conditions which are fulfilled by Schrodinger wave function. So under this topic, we are going to discuss Schrodinger time-independent wave equation as well as Schrodinger time-dependent equation. So that is a layout of today's lecture. Now, before going into detail of this topic, that is Schrodinger wave equations, let's try to understand the origin of these equations, that from where this Schrodinger equation has started. So actually this journey has started with the dual nature of light. As you all know that light shows dual nature. Sometimes light shows particle nature, and there are certain phenomena which are actually the evidence of wave nature of light. So light is having dual nature. Light shows particle nature because light supports photoelectric effect, Compton effect, and only if you will consider light as a particle, you can explain photoelectric effect as well as Compton's effect. As you also know that light shows interference phenomena, diffraction, polarization, and if you will consider light as a wave, only then you can say, only then you can explain these phenomena of interference and diffraction, and polarization. It means light is having dual nature. So on the basis of this dual nature of light, de Broglie, in his PhD thesis, he proposed that whenever we have a moving microscopic particle, that is also associated with a matter wave. Means a moving microscopic particle that is always associated with wave nature, or that particular wave which is associated with that moving material particle is known as matter wave. And we know from our knowledge of electromagnetics or light that whenever you want to describe wave nature, then in mathematical terms, in order to describe wave nature or in order to describe wave equation, we have second order partial differential equations. So basically a mathematical second order partial differential equation, that equation can completely describe wave nature. So since this matter wave, the concept of matter wave was generalized on the basis of dual nature of light. So we have a similar type of second order partial differential equation to describe the matter wave, to describe the nature of matter wave associated with moving microscopic particles. So basically what is this Schrodinger equation? The meaning is Schrodinger wave equation is actually a second order partial differential equation, and this mathematical equation will completely describe the matter wave, or you can say that will completely describe the wave nature associated with the moving microscopic particle. So whenever you have a moving microscopic particle, it is associated with wave nature. In order to describe that wave nature, Schrodinger, basically Erwin Schrodinger, that is the name of a scientist who proposed this equation. So this idea of second order partial differential equation, that was first time conceived by Erwin Schrodinger in 1926, and Erwin Schrodinger, for his contribution in quantum mechanics, he got Nobel Prize in 1933. So these equations are actually the contribution of Erwin Schrodinger. So what I was telling you, whenever there is a moving microscopic particle, that particle is associated with wave nature. If you want to describe that wave nature, then in mathematics, we have second order partial differential equations which can describe that wave nature. So whenever you want to describe any atomic system or the motion of moving microscopic particles, so Schrodinger wave equations, those equations will help us to describe those atomic systems. As in case of light, to describe the wave nature, we have second order partial differential equations in terms of E and H. So this Schrodinger wave equation, since your matter wave is different than electromagnetic radiations, so Schrodinger wave equation, that is not in terms of E or H. That equation was proposed by Schrodinger in terms of a new function, and that new function was again proposed by Schrodinger, and that function is known as Schrodinger wave function. So in 1926, Erwin Schrodinger, he proposed a second order partial differential equation in terms of a new mathematical function, and that function is known as Schrodinger wave function, and the notation for that Schrodinger wave function is psi. So this is all about the basic, or you can say the origin from where this equation has started. So Schrodinger proposed a wave function, and that wave function can describe the wave nature associated with a moving microscopic particle. And basically, there is a second order partial differential equation which will explain the wave nature, and that equation was proposed in terms of a wave function, and that wave function is actually a function of, that wave function is actually a function of space coordinates x, y, z and t. Means it depends upon position coordinates. Those position coordinates are x, y and z in 3 dimension. In addition to that, it also depends upon time coordinate. So the time when this wave function or this equation was proposed, it was purely a mathematical explanation for wave nature of moving material particles. There was no experimental evidence, experimental support for these equations. This was purely generalized on the basis of electromagnetic radiations. So you have a new function, and that function is Schrodinger wave function. And this equation, which is Schrodinger wave equation, that is also in terms of, that was also proposed in terms of that mathematical function, Schrodinger wave function. So now, before going into detail of the Schrodinger wave equation, first we will try to understand that what is the meaning, what is the significance of that mathematical function. So the role which is played by E and H in case of light, E is, that stands for electric field in case of an electromagnetic radiation, and H stands for magnetic field. So if you want to get any information associated with the electromagnetic radiation, you can extract that information with the help of E and H. For example, if you want to write the intensity of electromagnetic radiation, then that intensity is basically given by Poynting vector, which is cross product of E and H. So what I'm trying to say here, all the information associated with the electromagnetic radiation, that can be extracted with the help of E and H. Similarly, in quantum mechanics, every information which is associated with any atomic system, that information can be extracted with the help of wave function psi. So that psi plays the central role in quantum mechanics. So the variable quantity which characterize de Broglie wave is called wave function, and as I have already mentioned, this wave function is a function of space coordinates x, y, z. In addition to that, this wave function also depends upon time. The wave function that represents the variation in matter wave, it represents the oscillating behavior. It connects the particle wave nature and its associated wave nature. Already mentioned that this wave function will completely describe the wave nature associated with the moving microscopic particle. Now, at the time when this wave function was proposed, then at that time, this wave function, it was only known that wave function psi is a complex mathematical function. And later on, the meaning of this wave function was interpreted, and the complete meaning of this wave function is that when psi, the wave function, when it is multiplied with its complex conjugate, here the psi star is representing the complex conjugate of wave function. So the psi into psi star, that represents the probability of finding the particle. Means, if you have a microscopic particle, and if that particle is moving, it is associated with oscillating behavior, wave nature. Now that moving microscopic particle, we know that in quantum mechanics, that moving microscopic particle will be associated with the wave packet. Now, in order to describe that what is the probability of finding that particle, that can be obtained just by multiplying wave function with its complex conjugate. So, psi into psi star, that represents probability density. So, the probability of finding a particle in volume dB, which is dx, dy, dz, that is given by psi square. Basically, psi square is product of wave function and its complex conjugate. So, psi star into psi dx, dy, dz, that represents the probability of finding a particle in volume dB. And suppose you have an electron and that electron is moving around the nucleus. You know that electron is moving around the nucleus in a well-defined energy orbit. Now, at any point, what is the probability of finding that electron? That can be calculated just by multiplying psi with its complex conjugate. But you know the total probability of finding the particle. It is understood that your electron is somewhere within that energy level. So, the total probability of finding the particle is always 1, or you can say 100%. So, that total probability of finding the particle is represented by integration over psi star into psi. The psi square is basically product of wave function and its complex conjugate. So, psi star into psi, or you can say psi square dx, dy, dz, that is equal to 1. Integration is representing the total probability of finding the particle within this volume. So, psi star into psi dx, dy, dz equals to 1. This particular condition, which is saying that total probability of finding the particle is 1, this particular condition is known as normalization condition. And when this wave function satisfies this normalization condition, then this wave function is known as normalized wave function. So, what you have a moving microscopic particle. That moving microscopic particle is associated with wave nature. If you want to describe that wave nature in mathematics, you have second order partial differential equation. And that equation was proposed by Schrodinger in quantum mechanics in terms of a new complex mathematical function psi. This psi is purely a complex mathematical function, itself meaningless. But when you are multiplying psi with its complex conjugate, that product is basically representing the probability density, the probability of finding the particle. And the total probability of finding the particle is always 1, or you can say 100%, that is known as normalization condition. So, that is the significance of your wave function. Now, there are certain conditions which must be fulfilled by this wave function. So, the first one, as you can see in this slide, that your wave function must be finite everywhere. Now, what is the meaning of this? When I am saying that wave function must be finite everywhere, as I have mentioned in the previous slide, that the product of psi and psi star, that represents probability of finding the particle. As you know, that particle is, suppose you have a certain box, and within that box an electron is trapped. Means you are sure about this point, you are sure about this fact that your electronic, or you can say your particle is definitely within the box. So, when the particle is definitely present within the box, it means the probability of finding the particle within the box, that cannot be finite. Means the wave function, which is when multiplied with its complex conjugate, that wave function is representing the probability density. So, that wave function, that must be finite, because if the wave function will take infinite value, then the probability of finding the particle, that will also take infinite value, which is not correct, which is not true. So, the wave function must be finite everywhere. Second one is, the wave function must be a single valued function. Now, the meaning of this is, if the wave function will take more than 1 values, then the probability of finding the particle is also having more than 1 values. Means at a single point, because of multi-values of wave function, at a single point there will be more than 1 probability of finding the particle, which is not correct, which is wrong. So, wave function must be a single valued function. So, that is the second condition which must be fulfilled by the wave function. Now, the third one, wave function must be continuous. Now, the meaning of this continuity is, Suppose you have a microscopic particle which is approaching towards this barrier from this particular side. So you have a boundary over here and another boundary is present at this position. So the meaning of continuity is there should not be any break, there should not be any discontinuity over the boundaries. Means if the wave function in this region is psi1, the wave function in this region is psi2 and the wave function in this region is psi3, then over this boundary, the wave function for this psi1 and psi2 that will take same value. And over this boundary, the wave function psi2 and psi3 that will take same value. No discontinuity over the boundaries. So wave function must be continuous. Means over the boundaries, there should not be any discontinuity. And the first derivative that also exists and it will also take same values over the boundaries. So that is the meaning of continuity or continuous behavior of this wave function. Now the last one is that that wave function must be normalizable. So you know what is the meaning of normalizable. Normalizable means the total probability of finding the particle. So suppose your particle, microscopic particle, that is confined in a three-dimensional box, and A is the width of box along x-axis, B is the width along y-axis, and C is the width along z-axis, and your particle is trapped within that box. Then the meaning of normalization is that total probability of finding the particle within that box is represented by psi star into psi, and that total probability that should be 100% because your particle is definitely present within that box. So this is the meaning of normalization condition. Means within the boundaries, the total probability of finding the particle is always equal to 1. So these are the conditions which must be fulfilled by wave function. So I hope up to this point everything is clear. So what I mentioned up to here, you have a moving microscopic particle. In quantum mechanics, according to de Broglie, that moving microscopic particle is associated with wave nature. In order to describe that wave nature, you have second order partial differential equation according to the proposal of Erwin Schrodinger, which was given in 1926. And that equation is in terms of a new mathematical function which is known as Schrodinger wave function. Schrodinger wave function is a complex mathematical function. It's meaningless, but when multiplied with its complex conjugate, it represents probability density. Wave function must be single valued, must be finite, must be continuous, and must be normalizable. Now we are going to write those Schrodinger wave equations, and these Schrodinger equations, as I have already mentioned, that the heart of quantum mechanics is basically these Schrodinger equations, because whenever you want to describe any microscopic system, then these Schrodinger equations will serve the purpose. They will describe that microscopic system. So that is the reason these Schrodinger equations, these second order partial differential equations, are very important. Basically, Schrodinger wave equations can be Schrodinger wave equation that can be written in two different forms. These two different forms are nothing new, but these are the two different aspects of Schrodinger wave equation. Now, why you need those two different equations? Let me explain that point first. Suppose you have a particle and microscopic particle. That particle is moving. It is associated with wave nature. In order to describe that wave nature, you have a second order partial differential equation. Now, two cases are there. If the energy of particle, that microscopic particle which is moving, if the energy of that particle is independent of time, means it is not changing with time, it is depending only upon position coordinates. In that case, the equation which will describe that atomic system, that equation is Schrodinger time independent equation. If you will solve that, you will get your wave function which will be totally independent of t. But in case number 2, if you have a microscopic particle and if that particle is moving and if the energy of that particle is changing with time, means at time t1 let the energy is E1, at time t2 let the energy is E2, and these two values E1 and E2 are totally different. It means your energy is actually depending upon time. In that case, in order to describe that atomic system, you require Schrodinger wave equation in a different form, and that equation is known as time dependent equation. So that is the major difference. If the energy of system is independent of time, then you will apply time independent equation, and if the energy of system is depending upon time, then you have to apply time dependent equation. But you have to remember this, that these two equations means you can easily derive your time dependent equation from time independent. So these equations are just the form of a single equation. Only difference is, in one of the equation your wave function will depend upon x, y, z as well as t, and in case of time independent, it will depend only upon x, y and z. So now I'm starting with your time independent equation. So your wave equation in general form, that can be written by this equation. This is a second order partial mathematical equation which will describe the wave nature. You can see here del square phi upon del x square plus del square phi upon del y square plus del square phi upon del z square equal to 1 upon c square del square phi upon del t square. This is a general wave equation. In order to describe wave nature, we have this equation. In this equation, you have this phi which is actually depending upon x, y, z and t. So this is general equation, but you know Schrodinger proposed that wave equation in terms of wave function psi. So this equation, now we are going to write Schrodinger general wave equation in terms of psi. So this is your general Schrodinger wave equation. Del square psi upon del x square plus del square psi upon del y square del square psi upon del z square equal to 1 upon v square del square psi upon del t square. In this equation, you can see the psi is a function of x, y, z as well as t. And one more interesting point is there. As you have seen that in general wave equation you have c square here, but in Schrodinger wave equation we have written 1 upon v square del square psi upon del t square. As you know, in case of quantum mechanics, whenever you have a moving microscopic particle, that particle is associated with wave nature, and according to de Broglie, that particle is associated with a matter wave. But later on it was observed that instead of a single matter wave, there is a wave packet associated with a moving microscopic particle, and that wave packet travels with the same speed as the speed of particle. That is the reason you have 1 upon v square here, right? So you have this general Schrodinger equation. Now our job is to write this equation in time independent form as well as time dependent form. So first you will write this equation in time independent form, and from there you will also get the time dependent form of Schrodinger equation. So in order to write Schrodinger time independent equation, what I am going to do now, I am going to write this wave function psi as a product of two functions, where the first one that depends only upon x, y and z, and the second part is depending only upon time. Now, why I am writing this? Suppose your wave function, this wave function that is of this particular form, I k dot r minus omega t. So now you can see in this particular term, this e raised to power I k dot r, this particular part is position coordinates dependent. It is depending upon x, y and z. And the second part, e raised to power minus I omega t, that is time dependent part. And if you will see carefully, you can also write this as e raised to power I k dot r into e raised to power minus I omega t. Means what you have done, you have separated both the parts. The first part is depending only upon position coordinates now, and the second one is depending upon time. So what I'm trying to say here, in mathematics, if you have a function which depends upon position coordinates as well as time coordinates, coordinate, you can write that function as product of two functions, where the first one is depending upon position coordinates and the second one is depending upon time. So I have done the same thing here. This wave function psi is a function of x, y, z and t. I have written this wave function as a as a product of two functions, where the first one are represented by psi, which is depending only upon position coordinates, and the second one is time dependent function. So I hope you can differentiate between these two psi's. This psi is a function of x, y, z and t, but this psi is a function of the psi with bold sign that depending upon x, y, z and t, and it is this one is depending only upon x, y and z. And when we are talking about wave nature, then basically this time dependent part that represents the periodic behavior, and its nature or the type of this function f, that will be either e raised to power I omega t or e raised to power minus I omega t. You can choose any of these two. You can take e raised to power I omega t or e raised to power minus I omega t. So we have taken e raised to power I omega t. So what you have, your wave function is now a product of two functions, where the first one is independent of t and the second one is independent of position coordinates. Now what you have to do, you have to differentiate this equation number 3. You will differentiate it with respect to x 2 times, then with respect to y 2 times, with respect to z 2 times, and with respect to time 2 times. Means you have to differentiate your wave function with respect to x, y, z and t 2 times. So if you will differentiate this psi, and why you are doing so? Because you have to eliminate the time dependent part. So you are differentiating this psi with respect to x. When you will differentiate it for the first time, it will be del psi by del x. This part will remain as a constant. This will remain constant, and you have to differentiate only this particular part. So this is del psi by del x. I can write it like this. Del psi by del x is equal to del psi by del x e raised to power I omega t. I hope the meaning of this psi and this psi is clear to you. The psi on left hand side, that depends upon x, y, z and t. The psi on right hand side, that depends upon x, y and z only. So differentiating psi with respect to x one time, you are getting this. If you will differentiate psi with respect to x second time, then there is differentiation of this psi only. This time dependent part will remain in the same form. So finally what you are getting, after differentiating with respect to x, you are getting del square psi upon del x square equals to del square psi upon del x square e raised to power I omega t. Again I am emphasizing on this point, psi with bold sign that depends upon x, y, z and t, whereas this is depending only upon x, y and z. Similarly, you have to differentiate this psi with respect to y. You will get a similar type of result. So after differentiating with respect to y, you are getting this result. And on the similar lines, you have to differentiate psi with respect to z 2 times, and when you will differentiate, you will get this particular equation. So what you are getting, after differentiating psi with respect to x, y and z, you are getting your equation number 4, 5 and 6. So differentiation with respect to position coordinates is done. Now we have to differentiate this psi with respect to t. So let's differentiate it. So when you will differentiate psi, I am differentiating it here. Psi is equal to psi into e raised to power I omega t. So in this case, this psi, since it is depending upon x, y and z, independent of t, it will serve as a constant. It will remain as a constant. Differentiating one time, you will get psi as it is, and differentiation of exponential, you know, that is exponential. So it is I omega into this particular term. Again, you have to differentiate. So when you will differentiate it for the second time, psi will remain same, but you will get one more I omega here. So this will be I square omega square, and exponential will remain same. So you know I square is minus 1. So finally what you have? You have minus omega square psi e raised to power I omega t. After differentiating psi with respect to t 2 times, you are getting equation number 7. I hope equation number 4, 5, 6 and 7, all equations are clear. What you have done, you have taken your equation number 3, then you have differentiated with respect to x, y, z and t 2 times, and you are getting 4, 5, 6 and 7. Now what you have to do in order to get that time independent equation? you have to substitute all these values in equation number 1. You have to differentiate, you have to substitute this from equation number 4, this from 5, this from 6, and this term from 7. So just substitute all these values in equation number 1, and after substituting, you are getting, basically you are getting this e raised to power I omega t, and you are also getting this particular term here after substitution in equation number 1. So since this e raised to power I omega t, that is a common factor, so it will get cancelled and you will get only this simplified equation, del square psi upon del x square plus del square psi upon del y square plus del square psi upon del z square equals to minus omega square v square psi. And the important point is, in this equation you have psi, and this psi is totally independent of time. It is only a function of x, y, z and t. And you all know del square upon del x square plus del square upon del y square plus del square upon del z square. This is our Laplacian operator, and this Laplacian operator is represented as del square. So what we have done here, we have substituted these three terms with this simple term del square psi, where all the three terms, del square upon del x square, del square upon del y square plus del square upon del z square, all these terms are there in del square psi plus omega square v square psi equals to 0. So now we have this equation number 9 here. Since we have to write that second order partial differential equation in time independent form, and as I have already mentioned that we will apply time independent equation only for those atomic systems where energy is not depending upon time. It means somehow we have to convert this term in terms of energy so that we can correlate it with the energy of the system. So for doing so, what we are going to do here, we know this omega can be written as 2 pi nu by lambda. So let me simplify this. Give me a second. Omega is 2 pi nu, and this omega, this omega is omega upon v is equal to 2 pi nu upon v. You know, product of frequency and wavelength, that is equal to v. So it means this 2 pi and nu by v can be written as 2 pi by lambda. And according to de Broglie, you know your lambda is equal to h upon p. So just substituting these two, you are getting omega upon v is equal to 2 pi h upon p. So h upon 2 pi, that is written as h cross. So omega upon v is simply p upon h cross. It means your omega square upon v square. If you want to write omega square upon v square, that will be equal to p square upon h cross square. So you have this omega square upon v square is p square upon h cross square. Now for any system, we know the total energy, that capital E is sum of its kinetic energy. Kinetic energy is p square upon 2m plus potential energy, right? And if you want to write p square from here, you can see just by simplifying this, you are getting 2m e minus v. It means this omega square upon v square, which is actually p square upon h cross square, you can replace p square by 2m into e minus v. So what you are getting, this p square as 2m into e minus v. Just substitute that omega square upon v square, v square as p square upon h cross square, which is further 2m into e minus v upon h cross square, where this E is the total energy of the system and capital V is the potential energy. So this omega square upon v square in terms of energy can be written like this. Now what you have to do, you have to substitute this value, this omega square upon v square in equation number 9, and after substitution, what you are getting? You are getting del square psi plus 2m upon h cross square into e minus v psi equals to 0. So this equation number 10, as you can see, it is a second order partial differential equation, and in this equation, this psi is a function of x, y and z, and this energy is independent of time. So you can see here that this equation, when you will simplify it, you will get your wave function which will be independent of t. So this equation is known as Schrodinger time independent equation. And for all those systems where the energy is not changing with time, you can apply this equation to simplify those microscopic systems. And if you have a free particle, then for a free particle, potential energy is always 0. So for a free particle, this equation will take this particular form, that is equation number 11. Just write this V as 0. For free particle, you will get del square psi upon del x square plus 2me upon h cross square psi equals to 0. This is our time independent equation. Now the time dependent equation, that is also a form of the same equation. So in next step, we will try to write this time independent equation in time dependent form. So for doing that, we have this particular derivation, this particular slide. So now we will write our time dependent equation. So I hope up to here, this point is very much clear that if the energy of particle is changing with time, only then you will apply this equation. If the energy of particle is not changing with time, then you will apply the equation which we have seen in the previous slide. So in order to write this time dependent equation, what you are going to do? You have a function, and that wave function is written as product of two functions. The first one, we have written that first part as psi naught here, where psi naught is depending only upon x, y and z. And the second one is time dependent function. And as I have already mentioned that this time dependent function is a periodic function, and that will take e raised to power plus I omega t form or e raised to power minus I omega t form, because we are talking about the oscillating behavior. So if you will take e raised to power I omega t, that will represent the oscillating behavior. If you will take e raised to power minus I omega t, again that will represent the oscillating behavior. You can take any of these two. So what we have done here, we have written this psi as psi naught, where psi naught is independent of time, and the second part, which is time dependent, that is taken as e raised to power minus I omega t. Now just differentiate this equation number 2 with respect to t. So when you will differentiate it with respect to t, then psi naught will remain in the same form, and the derivative of this term is minus I omega into this. So del psi by del t is psi naught, and this omega can be written as 2 pi nu minus I 2 pi nu e raised to power I omega t. You know the psi naught into exponential part, that is psi. So in totality, this del psi by del t is minus I 2 pi nu into psi. So that is your del psi by del t. And you know that E is h nu. So from here, frequency, linear frequency can be written as E by h. So your previous term was minus 2 pi I nu into psi. So that nu is replaced by E by h. So what you have now, del psi by del t is minus I, and you know h upon 2 pi is h cross. So this is minus I upon h cross E psi. It means from here you can write E psi as I h cross del psi by del t. So what you have done, you have just differentiated psi with respect to t, and from there you got an expression for E psi, and that is equal to I h cross del psi by del t. Now you know what is your time independent equation. So we have seen earlier that del square psi plus 2m upon h cross square E minus V psi equals to 0. That is our time independent equation. Now if you will substitute the value of E from here, just substitute the value of E from equation number 3. If you will substitute this, what you will get? Del square psi will remain as it is, plus 2m upon h cross square as it is. Now replace that E psi with I h cross del psi by del t, and this will be minus V psi equals to 0. So after simplifying, what you are getting? Del square psi, just multiply it here, and after simplifying you are getting this minus h cross square upon 2m del square psi plus V psi equals to I h cross del psi by del t. As you can see in this equation, if you will simplify it, this is a second order partial differential equation in terms of psi. And if you will simplify this, then this psi will be a function of x, y, z as well as t. Means this particular equation can be applied for those those atomic systems where the energy of particle is changing with time. So if you will simplify this equation, you will get your wave function in terms of x, y, z and t. So this is your time dependent equation. So you have two different equations. One is time independent, which is del square psi plus 2m upon h cross square E minus V into psi equals to 0. In this equation, psi is a function of x, y and z only. And time dependent equation is I h cross del psi by del t is equal to minus h cross square upon 2m del square psi plus v psi. In this equation, psi is a function of x, y, z and t. That is the difference. It is independent of t, whereas in this equation, psi is in addition to x, y and z, it also depends upon time. Okay, so these are your Schrodinger equations. Now these Schrodinger equations, these equations can be solved only for certain values of energy. Means there are only discrete values of E for which you can solve that Schrodinger equation. Therefore, the values of E for which Schrodinger equations can be solved, those values are known as energy eigenvalues. And the wave function corresponding to those energy states, those wave functions are known as eigenfunctions. So whenever you want to describe any atomic system, we require wave function. So in order to get those wave functions, we have second order partial differential equations. So Schrodinger wave equations are basically the main equations, are the heart of your quantum mechanics. Whenever you want to get information of any parameter related to a quantum mechanical system, you need these equations. You have to simplify those equations. You have to get the value of psi. Only then you can describe that energy, momentum or any parameter related to that system. Okay, so these are reference books for this quantum mechanics. So you can refer these books for Schrodinger equations and Schrodinger wave function. That's all for today. Thank you so much.